In this video, we're going to determine the irreducible representations for the sigma bonds here between the sulfur and the fluorines, as well as the pi bonds between the sulfur and the fluorines. And so the first step will be to figure out the point group of the molecule. So what we have here is SF6, and I've already given you the clue that it's in the OH point group, but if we go through the flowchart, the first question is it linear? No, it's not linear. The next question is, does it have multiple CN axes that are greater than 3? And it does. We can see already right here that we have one that's located through that plane, and then another one that goes through that plane. The molecule has more than just these two C3 axes. However, we don't need to concern ourselves with identifying those, as we're already past that step now. The next question is, does it have an inversion center? And it does, as this fluorine and this fluorine are equivalent, as well as this fluorine and this fluorine and this fluorine and this fluorine right here. The next question is, does it have a C5 axis? And no, it does not. And so we'll end up in the OH point group. And so now that we're in the OH point group, the first thing that we want to do is we want to generate the reducible representation of our sigma bonds. The first step is going to be to generate the reducible representation of the sigma bonds. And so to do that, what we'll do now is we'll start figuring out what the values are for each symmetry operation. So in the case of the identity, all 6 of these sigma bonds will remain intact, so we'll get a value of 6 there. In the case of a C3, if we just use this C3 axis right here, what we'll see is that that C3 axis is going to move all of the sigma bonds, and so we'll stay with a value of 0. The next one is the C2, and so this is not the C2 that is the same as the C42, but rather the C2 that bisects the fluorine-sulfur-fluorine bonds. And if we perform this C2 operation, all of the bonds rotate. In the case of a C4 rotation, right here, we can see that these 4 bonds move. However, these 2, the ones for the axial positions, do not, and so we end up with a value of 2. For the three C2s right here, so the same as the C42, what we'll end up seeing is that we'll have an equivalent value, as all 4 of the equatorial bonds will move, but the axial bonds will remain intact. If we perform an inversion, all of the bonds move. Same with an S4 operation, as if we perform a 4-fold rotation and then a mirror plane, we'll see that all of the bonds have moved in that case. S6 is the same. If we perform a sigma H, it will contain, in this case, these 4 bonds right here, but these 2 axial bonds will move, so we will get a value of 4. And then in the case of the sigma Ds, so the mirror planes that don't contain all of the 4 bonds, but rather bisect the fluorine-sulfur-fluorine bonds in these cases, all we end up with are 2 sigma bonds that remain intact. So now that we've generated our reducible representation for our sigma bonds, the next step will be to identify what the irreducible representation is for the sigma bond. So we've done these types of exercises before, but I just wanted to go through it again. And so if we do that, in this case, what we can see is that when we work our way through, right here, we can see that if we multiply 1 times 6, we'll end up with a value of 6. 8 times 1 times 0 is 0. 6 times 1 times 0 is 0. 6 times 1 times 2 is 6, or it's a correction, is 12. Three times 1 times 2 gives us a value of 6. These will all stay zeros right here. So 3 times 1 times 4 gives us a value of 12. And then 6 times 2 gives us a value of 12 as well. And so this right here is our A1G. If we then divide it by the order of the group, which is 48, what we'll see is that 6 plus 12 plus 6 plus 12 plus 12 equals 48. And so our sigma bonds have A1G symmetry. Now if we go through the rest of the list, we can go through it again, and now we can do the A2G. So if we go through that same process again, we can just easily right here change some of the signs, and so we can see that the 12 now will become negative, the 6 will remain the same, this 12 will remain the same, this 12 will become negative. So if we do that, we can see that we end up with a value of 0 in this case. If we then move down next to the EG, what we can see is that we will then now have to multiply this value by 2. This value will become a 0. This value will be multiplied by 2. This value will be multiplied by 2 as well. And then this value will become 0. So if we add all of this up, what we will see is that we end up with 48 again. And so we know then that EG is the symmetry of another 2 sets of sigma bonding orbitals. If we keep on moving our way down and continue to do all of these for all of the different groups, what we will finally end up with is that the last 3 orbitals that are remaining will have T1U symmetry. And so if we go to the T1U, which is all the way here at the bottom, we can see it right here. So if we just calculate our way through again, what we will see is that if we multiply 1 times 3 times 6, we'll get 18. This value will stay 0. This value will stay 0. We will get 6 times 1 times 2, which gives us 12. We have 3 times minus 1 times 2, which gives us negative 6. These will then stay 0. In this case right here, we have 3 times 1 times 4, which will give us a value of 12. And then finally, we have 6 times 1 times 2, which gives us a value of 12 again. And so if we add all of this up, we'll end up then with a value of 48. And so the next step, now that we've determined what the irreducible representations are within the sigma bonds, is to determine the irreducible representations in the pi bonds. And so to do that, the first step is going to be to multiply our sigma bonding reducible representation by the X, Y, and Z irreducible representations. So with an OH, it's very easy because the irreducible representation for all 3 of those axes is actually T1U. So all we have to do is just multiply T1U by the sigma value. In other situations, you would just have to add up all of the individual irreducible representations that have the X, the Y, and the Z components. And so if we do that, right now what we'll see is that we will get, in this case, 3 times 6 is 18, 0 times 0 is 0, minus 1 times 0 is 0, 1 times 2 is 2, minus 1 times 2 gives us minus 2, minus 3 times 0 is 0, minus 1 times 0 is 0, 0 times 0 is 0, 1 times 4 is 4, and then 1 times 2 is 2. And so what we have right here now is the reducible representation for both the sigma and the pi bonds. And so to only get out the pi bond irreducible representation in this case, all we have to do is we just have to subtract out the sigma irreducible representations that we already know. And so if we do that, what we will then get is the pi reducible representation. And so if we subtract out the sigma, what we'll get is a value of 12 under E. If we do 2 minus 2 is equal to 0, minus 2 is equal to minus 4, 0 minus 0 is 0, 0, 0, 0, 0, 4 minus 4 is 0, 2 minus 2 is 0. So the reducible representation for the 12 pi bonds that we have is this right here. And so if we now go through and we do the entire process again of identifying what the irreducible representations are, what we can then see is that in the case of A1G, if we multiply 1 times 1 times 12, we get 12. These are all zeros, so they don't matter. If we do 3 times 1 times minus 4, we get minus 12. And then the rest are all going to be zeros as well. And so we can see 12 minus 12 is going to give us 0, so A1G is not present. And so to make things easier, because there are really only two numbers that we have to look at, we can just go through the list. And so we can see that in the case of A2G, both of these remain positive. In the case of EG, both of them are positive. In the case of T1G, we can see that we now multiply this value by 3, and so we get 36, and we have a negative 1 right here, and so then this becomes a positive 12, and so we can tell that for the for the pi bonds, T1G is one of the symmetries. And so if we go then down to the T2G, we can see again we have a positive value of 3 and a negative 1 in this case. And so that'll add up to 48, and so we will then also have one set of T2G orbitals. If we move our way down, A1U only has a value of 1 right here, and this remains positive. And we can go all the way through, and then as we can see, T1U and T2U have the correct characters for us to have the irreducible representations in this case. And so T1U plus T2U. And so these are the orbital symmetries that'll provide the sigma bonds and the pi bonds in the case of sulfur hexafluoride.